This video presents recent work on deformable object manipulation at the Sigma Clermont Institut Pascal. This is the outline of the video, with timestamps for each of its parts. We will first briefly introduce Sigma Clermont and Institut Pascal. Then we will present some of the recent research work on the manipulation of deformable objects. Institut Pascal is a joint interdisciplinary research and training unit in Clermont-Ferrand in France. It is under the supervision of three institutions: Sigma Clermont, which is a school of engineering, a University of Clermont-Auvergne, and CNRS. Three of the organizers of the workshop are members of Institut Pascal: Miguel Aranda, Juan Antonio Corrales, and Josep Mesoar. Within the structure of Institut Pascal, we are part of the ISPR department, which stands for Image Perception Systems and Robotics. Institut Pascal is involved in multiple research and development projects on the topic of manipulation of deformable objects, both at the French level and internationally. We are particularly interested in the application of this research to industrial tasks. There are two ongoing projects at European level coordinated by Sigma Clermont. One of them is the H2020 project SoftmanBot, and the other is the project COMMANDIA from the Sudoe Programme. I'm going to discuss some work on monocular shape tracking and servoing. We address the problem of shape servoing, which means controlling the shape of a deformable object with robots using sensory feedback. In particular, we want to do servoing of the full 3D shape of the object with a monocular camera. The main challenges here are inferring the 3D shape of the object from monocular images, the presence of visual occlusions, the high underactuation in the control of the shape of the object, and the fact that the deformation is difficult to predict accurately. Our main idea is to use a template, which is a model of the deformable object. It contains three elements: the rest shape of the object, a deformation law, and a texture map. We assume the deformation is isometric, which corresponds to objects of interest in practice, such as paper sheets. This is a diagram of the scheme we propose. We have a monocular camera and robots manipulating the object. Each robot is rigidly coupled with the object and fixes a rigid patch on it. We exploit this coupling both for perception and for control. We have a current and desired shapes of the object. These are inferred from monocular images, and we propose a control strategy to move towards the desired shape. The two main blocks we have are shape perception and shape control. For shape perception, we propose to track the current 3D shape using a shape from template algorithm that we adapt to the robotic manipulation scenario. The adaptations that we propose allow to track the shape fast and with robustness to occlusion. For shape control, we propose an algorithm based on a prediction of the evolution of the shape using the deformation law in the template. In this video, we show several examples of the proposed approaches for shape tracking and servoing. You can find more details about this work in the paper, which is presented in the main conference.
Hello everyone, my name is Mohamed Reza Shatab and I'm a new PhD student in University of Clermont-Auvergne. I'm a member of a team in Pascal Institute and Sigma, which works mainly on robotic manipulation of deformable objects. It's a pleasure for me to present my work in this workshop today. It's a pity that we cannot meet in person. However, I put my email address at the bottom of the slide. If you had any question or comment or even any suggestion for collaboration, please don't hesitate to contact me. The work that I want to present today is the extension of a previous study which was published in this conference, and you can see the reference at the bottom of this slide. In that work, we introduced a new algorithm called Fast Particle Shape from Template, or Fast Particle SFT, to track the isometric deformation of the thin shell object. The algorithm was fast, wide baseline, and robust to occlusions. However, the limitation was it could not be implemented to surfaces with real texture, because the tracking points should be exactly located on the template grid, and this is not what we can track when dealing with real surfaces with arbitrary texture. Solving this problem, we developed a new algorithm. The algorithm covers the whole pipeline from the feature detection and matching to reconstructing the 3D shape, and all of them will be performed in real time. First, the features in the template and in the image will be extracted and matched together using a relevant algorithm like SIFT. Then the outliers will be removed using a new outlier removal algorithm that we developed. It can deal with a high percentage of outliers. This enables us to use it without any sort of previous training for choosing the most recognizable matches or detaching the image from the background. Having all the correct matches after removing the outliers, now in the image registration step, we can calculate a warp function to transfer the flat grid from the template to the image space, and finally use that as the input for the SFT algorithm. In this video, you can observe the output of the full pipeline. It needs no previous training, just a template of the thin shell object and the images coming directly from the camera. It can cope with large deformations, occlusions, and self-occlusions. It is wide baseline, no tracking is used, and so it is robust to losing the image of the object in one or several frames, which can happen due to occlusions or even video cuts. By now, the execution speed of our algorithm for the full pipeline is up to 12 frames per second, but we are working on that to make it even faster, up to 30. In the next steps, we are going to extend this algorithm to non-isometric deformations, and after that, volumetric objects. Thank you for your attention.
Hello everyone, I am Rohit Chandra and I'm working as a postdoc researcher in Software on Board project with Sigma team in Clermont, France. I'm going to present my work, Shape Control of Linear Deformable Objects using Dual-Arm Robots, which was done under the supervision of Professor Juan Antonio Corrales Ramon and Professor Yusuf Mezwar. In this work, we used the concept of dual-arm coordination and applied it to obtain a desired shape for linear deformable objects. The presented approach adapts well to two kinds of material: elastic materials with uniform medium stiffness, for example, a linear bar of foam, and highly flexible objects like rope. The effect of gravity on the shape of the objects are assumed to be negligible. Elastic materials with medium stiffness were manipulated by applying the concept of virtual sticks, which is one of the most common approaches to model dual-arm coordination for static and quasi-static manipulation of rigid objects. The shape control of highly flexible materials under kinematic constraints were modeled using virtual mechanisms. The novelty for both kinds of shape control lies in the use of screw theory for the modeling of manipulators and for the modeling of virtual mechanisms, along with its representation using dual quaternions. Such a strategy leads to computational and storage efficiency and ease of modeling of mechanism, in addition to natural consideration of relative rotation between the arms, and thus improve performance for faster operations compared to existing approaches. In this video, the ends of the virtual stick are pointing towards the center of the foam, and a relative rotation along an axis perpendicular to the object is provided by the two arms. In this video, the tips are pointing at a new location away from the center for generating a desired shape. If the object has enough stiffness, more complex shapes can be generated. Here, we were able to achieve an S shape by moving the tips of the virtual sticks successively. This kind of strategy can be useful for manipulating objects for packaging purposes. In this experiment, we achieved a U shape with a rope that is being manipulated under physical constraint. The constraints were represented using serial mechanism with two rotational joints. Along with the generation of relative motion using virtual mechanisms, we were also maintaining the same absolute position, that is the center of the rope, throughout the operation. We achieve S shape in this experiment with the same mechanism but by giving opposing rotation to the two joints of the virtual mechanism. In the future, we would like to close the shape control loop with vision to obtain the ends of virtual sticks for the first strategy and the definition of virtual mechanism for the second strategy to represent the kinematic constraints. Thank you.
Now I will briefly present recent work on multi-robot coordination for deformable object manipulation. The motivation for using multiple robots is that they increase manipulation capabilities and are useful to transport or manipulate large or heavy deformable objects. The idea behind this work is to coordinate the motions of a team of robots using the concept of geometric deformation. In particular, we assume there is a desired state or shape of the team, and we move the robots to minimize a deformation measure relative to that shape. This measure is defined as the error of the optimal alignment between the current and desired team shapes. We have mainly focused on a 2D scenario. So we are not controlling the shape of the object, but the deformation of the object and of the team are related, and the approach we propose creates closely coordinated motions and is robust to perturbation. And for instance, when there is no sensing of contact forces, or when the shape of the object cannot be perceived reliably, moving the robots based on a concept of deformation can create safer motions. This approach can be interesting in different scenarios, such as transportation, manipulation with many robots, or controlling the fingertips of a robotic hand. We have explored the different ideas within this general framework. For instance, we have defined the decoupled controls that can allow the team to rotate, translate, and change its size while minimizing the deformation measure. We have also proposed leader-based approaches, and we have also included a control component to constrain the deformation to be affine, which can help to obtain a safer transition towards the desired shape. On this topic, we have published a conference paper, and we have a journal submission under review. I am going to discuss some works on manipulation of deformable objects based on force sensing and finite element modeling. Many tasks with deformable objects require sensing online the shape of the object. This problem is well known to be very challenging. In many cases it requires the use of visual markers, but still there are always visual occlusions that make it very difficult to perceive fully the state of the object. The main idea behind these works is to track the shape of the deformable object using force sensing without relying on visual sensing. This force is the force perceived due to the manipulation of the object by a robotic hand. The force is measured by tactile or force sensors. The proposed approach works by coupling the measured force to a deformation model of the object based on finite element method. Then this deformation model outputs the new shape of the object. The force sensing can come from tactile sensors. In this case, a recurrent neural network model was proposed to map the tactile readings of the sensor to forces. Alternatively, a force torque sensor was also used. In addition, an observer based on recurrent neural networks was proposed to estimate the non-contact forces. This was used to filter these forces out of the force input provided to the deformation model. The proposed shape sensing pipeline was also applied to a task of manipulating an object controlling its deformation. The video first shows deformation sensing experiments displaying the shape estimated with the simulated model. Now the video shows results of controlling a pose on the object. Thank you for your attention, and don't hesitate to send us an email in case you have any questions, suggestions or comments.